So last time, I think today we are going to study section 43, partial derivative, right? So last time we recall for function of one variable, we can compute the first derivative, second derivative, and so on. So we can, continue to differentiate this function as many as times you want, right? But today, our function is not only has one variable. Our function, for example, we have function of two variable, or function has three variable, or even for function with 100 variables. So for this, how do we define the derivative? So let's first write outside. If we have a function, okay, from a subset in R2 to R is a function. So in general, we write it as in this form. If f x y, how do we think about this? So let's introduce the definition. So here we have two independent variables, right? So let's first fix y. So mean that y is fixed, right? And then after y is fixed, you can think your function as a function of one variable because y is fixed. Okay, or you can rewrite it as g x is f x y. So you have to keep in mind that y is fixed. It's kind of by this technique, finally you get a function of one variable, right? For a function of one variable, we knew how to compute the derivative. So we can have gx. For any y, you compute this, but for example, here, y is fixed, but y can be any number. It's kind of every time you fix the number and then you do this process. So we compute the derivative. For this case, you can compute the derivative for gx, right? Okay, so, and this is defined as f partial x and x, y. So this is called the partial derivative. Partial derivative of f in terms of x, or notation for this. In general, the people will write, okay, f x or f x x y f1 x y, or sometimes people just write f1. This is partial x x y. If you look at a different textbook, they may use different notation. You may say, why do you write f1? Because f is the first component. It's kind of just the convention. Don't ask me why, because there is no reason, just a convention. Okay. So in the future, the people write any of them, you have to understand what does he mean by that. Okay. So this is called the partial derivative in terms of x. Okay, this is the first part. It's called the partial derivative. And then we do the same process. So then let's stop video. Let's fix x. And then we have y to f x y. The same, we can rewrite it h y, which is f x, y, just keep in mind y, x is fixed. Okay, we can compute the derivative for y, right? And this is defined, is written. You can always compute this. This is right as partial y or xy. For example, you may, you know, if I write in this way, you may say, okay, it's hard to understand. But, you know, just, you know, we are talking. In general, this means that the definition of partial y, the same as for partial x, is hy, but, right? The same notation. So some people write fy and fy xy, which is f2 xy, or just write f2. All of them are partial y, partial x, or xy, right? If you ask me, what's this? This is just this. But, you know, when you are doing a problem, you don't have to write this because there's no process here. I'm just introducing this. That's why we have hy. When you are doing problems, there is no h and g. So hence, after this introduction, we have fx, fy are called the partial derivative of fxy with respect to, or in terms there with respect to xy respectively. Okay, so just this. So this is about the partial derivative. If you think it in this way, it's kind of, you know, easy to understand. You just fix one and compute the derivative for another one. I think that's the idea. Okay, so let's look at examples. Okay, so now we have a function fxy, which is x cubic plus x squared y squared minus 2y squared. The problem is that find fx21 and fy21. Okay, so what do I mean by this? Means that compute the partial derivative of fx, or in terms of x, and then evaluate the partial derivative at point 21. The same for fy. So before I start, I only emphasize something. By my experience, you know, sometimes, you know, just there are always some students, you know, I don't understand him or her. It's kind of there are some students who always, you know, plugging this number into this function, and then he get a number. So then he said, okay, the derivative is 0. If you do it in this way, everything is 0. We don't have to study, because you just plug in that number, you always get a number, and then the derivative, you compute the, you know, derivative, you always get a 0. Nothing to do, right? I hope you guys don't make this kind of mistake. You know, this kind of mistake is quite stupid, you know, you have to avoid it. So the first step is you compute fx. So when you are computing fx, you, in your mind, y is a constant because y is fixed, x is a variable. You do this like you did for function of one variable, just the x is a variable. So this is 3x squared. Just remember, y is a constant now. So x is a variable. So you get 2x y squared, because y is a constant, right? The derivative of this term is 0 because y is a constant. We are differentiating x. So we get fx So, and then let's compute Fy. For this, X is a constant. So you differentiate X power to 3, you got 0. Maybe just write at 0. So you differentiate Y, X is a constant. So we get a 2x squared Y. Okay. For last term, for Y, so we have fxy is 3x squared plus 2xy squared, fyxy, which is 2x squared y minus 4y, and fx 1, you just plug in this number, 3 multiplied by 4 plus 2 multiplied by 4 plus 1, we get 12 plus 4 is 16. Okay, fy21, plug in this number, is 2 multiplied by 4 multiplied by 1. I hope so. Right? Okay, minus 4 minus multiplied by 1, we get 8. Right, I think I'm right. Minus 4 is 4. So the answer is fx21 is 16, fy21 is 4, right? So this is this problem. You generally have to know how to compute the derivative. Calculus includes 2 parts, integration and the derivative. If you don't know any of them, I think you can say, oh, you didn't. I can say you didn't study calculus, right? So this is about the partial derivative. You just think it in the way as you studied for function of one variable. You know how to compute it and how to apply it for the future. Okay. Because I'll give you some application later. Okay. So let's continue. So you may say, okay, why do you introduce this? What's the meaning of what's the meaning of partial derivative? Okay, let's look at the definition of the partial derivative. Like we know f x at any point, right? So first, let's look at the definition. Okay, so this is, okay, let me give you more, because probably you may think I jumped too much. Actually, I'm not. Okay. G x is f x y. Now y is fixed. And then we know gx is at the point of a limit. Okay. Now let's focus on the point A, B, and then we compute GA. By the definition, this is X approach to A, GX minus GA, right? X minus A. And then we plug in this X approach to A, F, X. You know Y is fixed, right? We are talking about the point of B, so means that Y is B minus F A B, right? And over X A. By the definition, this is F X A B, which is limit X approaching to A X B subtracted by A B over X by A. This is the the definition, mathematical definition, or strictly definition of the partial derivative. So let me draw a picture for you. What do I mean? What does it mean? This. So we draw the graph of f like this. So this is A, B. This is the value of f, a, b, right? At this point, from this, we can say B is fixed. It's kind of when you are draw a picture, this is B, this is A, right? So we are in R3, right? This is X, this is Y direction. B is fixed, mean you know, B is fixed, mean X is changing, right? No. Yeah. We can say, okay, if we have a line close to this line will be mapped to a curve in this space, right? Right. So we get a curve. Next this, we map this to this curve. Y is fixed. You know, means that Y doesn't change. This is just a curve, right? Okay. And then we compute X is changed. So what do I mean by this? Fx, by the geometric meaning of derivative, Fx evaluated at A, B is just the derivative or the slope of the, the tangent line to this curve, right? So Fx AB is the slope of the line, the curve here. Actually, there is a name for this. This is called the X curve. Just a name, because that's an image of the x-axis, right? So that's a geometric meaning. Like what we did for the function of one variable, right? The derivative is just the slope of the tangent line, right? By the same method, okay, by the same method, you can, analyze Fy, right? For Fy, okay, the question that, always something common, just 1 minute or 2 minutes and left, because the room has the, function to record how long have you stay here. Okay. So the same for Fy, now X is fixed. This is Y, right? And then the Y-axis maps to a curve like this. This is, now I give it a name, Y curve. And then by what we know before, this Fy is just the slope of the tangent line. So this is the geometric meaning of the partial derivative. Okay, that's what I want to say for the derivative. So, and then you can think this as a exam remark. It's kind of in the book. It doesn't emphasize it here, but we will use it later for the tangent plane. Okay. So let's look at more examples. So now have Fxy equals to sine x over x plus y. So let's compute this Fy and Fx. So let's first compute Fx. So when you are calculate the partial derivative in terms of x, you just pretend y is fixed. So now this function is kind of complicated, but it's still easy. So first, we think this as a whole, right? We have cosine x plus y, right? And x plus y differentiate it in terms of x, right? This is about the chain rule. You may say you didn't study it. No, you studied it. Just y is a constant. There is only one variable. We don't have two variables now. Because we are doing this, you always keep in mind when you are computing the derivative in terms of x, y is fixed. When you are computing the derivative in terms of x is no y, x is fixed. So you have to think in this way. Otherwise, you are in some trap. You don't know how to think about it. So we get a cosine x over x plus y. Now y is a constant. So let's compute the derivative in terms of x. Y is a constant. So in terms of x, you get 1 and multiply by x plus y minus x. Differentiate this is 1. The derivative of x is 1. The derivative of y in terms of x is 0. That's why it's 1. So this is cosine x plus y. And try to simplify this. So what's this? This should be y over x plus y squared. So I will write it in this way: cosine x plus y over x plus y squared. So this is fy. So you have to know how to compute the partial derivative. Fy by the same method. So x is fixed. Okay. Cosine x plus y. X is a constant. Y is a variable. X plus y and y, right? So cosine x plus y. So multiply by x plus y complete square. X, if you differentiate in terms of y, which is 0, multiply by x plus y minus x, differentiate this term in terms of y, you get 1. So finally, we get negative x plus y squared cosine x over x plus y. Okay. This is about fx and fy. Oh, I think I'm right. I don't have too much say about the computation, because you just follow this step. You may say, if you don't know this problem, you don't understand me, you just go to do more problems and try to figure out, because it's very straightforward, no any trick. Okay, so one more is about the application of the partial derivative. So let's look at one more example. So if z is determined by the equation x power to 3 y cubic plus z cubic plus 6xyz equals to 1, right? So, but like what I said, let's say we have x, y, z, 3 variables, right? And 1 constraint. After this, generally, we have 2 independent variables, 1 dependent variable, right? Because 1 constraint reduces the independent variable by 3. Oh, no, sorry, by 1. And then means that you have 2 independent variable. Automatically, we can ask, okay, what's partial z, partial x, or partial y, partial z? So it's kind of, you can say we have 2 variables, 2 independent variable, 1 independent variable. We can assume z is the dependent variable, right? And x, y are the independent variables. Kind of they can be written as in this format, right? Okay. So you may now you may say, oh, do I have to compute the z x y, z equals to z x y? No, if you look at this, I don't know how to compute z, z equals to z x y. I don't know. So you have to learn some trick to study it. So by this analysis, we can always write like in this form, rewrite this x power 2, 3, y power 2, 3, z power 2, 3, and write it as in this form. You just pretend you knew it, and plus x, x, y, z, x, y equals to 1. For example, let's differentiate it in terms of x. So we get 3 x power to 2 plus 0, because y is independent of x, right? Y is also an independent variable, plus 3z power to 2 or squared. But now z is a constant of, no, z is a function of x. So you have partial z, partial x. And then we differentiate this part. So we get x, y, z, because x is a variable, right? Keep the y there. And by the product rule, we have x, x, y, z, x. We get there. And then you put the two terms together, we get 3z squared plus 6y partial z partial x is equal to negative 3x minus 6yz. So zx is negative 3x or minus 6yz over 3z squared plus 6xy. So this is zx. Okay, to be honestly, you can compute the zy directly. If you look at this formula, you can say x, y has the same position in this equation. So you can rewrite it. This is 6, 3y squared minus 6xz over, 3z squared plus 6xy. Because you just replace all the x by y, replace y by x, you get answer. You may say, why do I jump there? You can compute it by yourself directly because the method is the total same, right? You have to do some problems like this, otherwise, like I said, listening is not enough. Okay, so this is called, is kind of the application of implicit function theorem. Okay. So let's go more. Just show you more examples. That's what I can do today. And then let's look at an example. Before, we only talked about fxy. For it, we have fx, fy. Now, automatically, if we consider this, right, we have fx, fy, fz. I don't think I have to explain this, right? When you are considering fx, you fix the yz. When you are computing fy, you fix the xz. When you are computing fz, you fix the xy, right? So let's look at an example. it's quite straightforward. Even I don't know what I can explain. Nothing needed to explain. Okay, this is f x y z, which is e x y ln z. So let's first compute the fx. In general, I will not write x, y, z component here. You just write this. For example, if some problem is asking to evaluate at some point, okay, you write it outside. That's okay. In general, you don't have to write this outside because it wastes the time. So we get a x. So when you're computing fx, y is a constant. So this is a constant. So we only need to care about this part. This is e x y, right? X is a variable, y is a constant. So we differentiate this part in x, we get a y, and then we get a ln z. So the answer is y ln z, right? And e x y. So, and then let's compute the f x y z. This is f y. We compute the derivative in terms of y. So this is e x y, and differentiate this part, we get x, right? We get ln z, and then we get ln x z, and e x y. Let's look at the last one, f x y z. This is f z. So e x y just copy, because in this case this is a constant, and the ln z, if you differentiate it, you'll get 1 over z. So the answer is e x y over z. Right. Okay. This is about the first partial derivative of first order. Okay. And then, like what we studied, for function of one variable, after we compute this, we compute the first derivative. Here we compute the fx, fy. If you have 3 variables, you compute the 4 variables, right? 3 variables. And then for function of one variable, we also compute the second derivative. But here, okay, if we are talking about the function of 2 variables, okay, you get at least 2 functions, right? This is a function, this is a function. They are independent of each other, just get 2 functions. Okay, or if we are consider function of 3 variables, we have fx, fy, and fz, right? We have 3 functions. So we can now think fx as a function, go more. So now fx is a function. This is the partial derivative. And then for this, we can continue. This is a function, right? We compute another derivative. We call it partial x. This is a partial x, f x, or I write more partial fx. That's just a notation. Okay, this is a function. We continue to differentiate it in terms of x. We get fx, and then fxy. This is a partial y, partial x. This is a partial y, partial x. Maybe some people doesn't read it partial. I think maybe some people use del, or some read it partial. Anyway, both are okay. Okay. This just this del or partial. Okay. Okay. Let's, and also for fy, we can define fyx, fyy. This is a partial x, partial y. This is a partial x, partial y, right? This is a partial y, partial f, partial y. No. I jumped. Anyway, I just write a lot of, help you to get familiar with this notation. y, partial y. You know, sometimes the book just write, okay, partial y x squared, right? Partial y, partial x, partial 2x, partial y, partial times 2, partial y squared. You know, this is just a many notation. It's not my fault, just we have to have so much notation. So this is the second derivative of function of two variables. We got a full function, right? But a full function of one variable, we only get one, but now here we have full. In general, we can write as fx, fxy, fyx, fyy. We put it as a box or matrix. This is called the Hessian of f. Okay. So let's go more. If we have function f, x, y, z, by the same method, we can define the f, x, x, f, x, y, f, x, z, f, y, x, f, y, y, f, y, z, f, z, x, f, z, y, f, z, z. You get a 9 function. You put them together. You get, this is also called the Hessian of f. Right here we have fx, fy, fz. I just give a name. This is called d. This is called the gradient of f. Here we have gradient. No, sorry. D is fx, fy, like this. This is called the gradient of f. 1, 2, 1, 2. Automatically, you can generalize this for the function of 3 variables, 5 variables, 10 variables, 100 variables. Right, it's the same. Okay. Okay. And also sometimes the people write fx as f11, fxy, f12, fyx is f21, fyy is f22. Just the notation as we did for the first partial derivative, partial derivative of first order. They are the same. Okay. Just the many notations. But here you have to be careful. Let me cross out something. You can say this, 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 and this. So let's focus on this. Right. You first differentiate fx, differentiate x and then y. And you differentiate x first and then y. The problem is, what's the relations between fx and fy? Yeah, that's an automatic question, right? So there is a theorem. Okay. Says. Okay. There is a theorem. Says. There is a theorem. Explain this. If fx, fy, if we know the first derivative is continuous, right? If the first derivative is good, you don't have to think about this. In the future, in our class, course, fx, fy are always continuous. Otherwise it's too hard. Okay. If this is good, we always have fxy and fyx. Okay. After we knew this, so means that for the Hessian, we have 4 functions. Actually, when you are doing a problem, you always know the dialogue, they are the same. This direction, they are the same, right? You only have to compute fxy or fyx. The same, this theorem also apply for the same theorem. If f, x, fy, fz are continuous, fxy is fyx, fxz is fzx, fyz is fzy. So they are the same. They are the same. They are the same. So means that you only have computed this part, this part, this part, this part, this part, this part. They are equal to. These three are equal to these three. Okay, in general, when you are doing a problem, we only test your function of two variables because three variables we need some linear algebra, but sample you may not study linear algebra. Okay, so let's go more. I'm almost done. So let's look at one more example, fxy example. This is x 3 plus x squared y minus 2y squared. Let's compute fx 3x squared plus 2xy cubic minus 0, fy is 0 plus 3x squared y squared minus 4y. And then for this, we compute fx and x. We get 6x plus 2y cubic. fxy 0 plus 6xy squared. For this, we compute fyx, right? This is 6xy squared. fyy is negative 4. So you can say they are the same. The first derivative are continuous, right? So anyway, you have to, like in general, like that theorem, you have to keep in mind. You may say, I don't want to remember it. No, we are doing a problem. If you can compute the latest derivative, you save time. You save time, right? Why not? Right. Okay. So this is about the last example. And then we're almost done. Next example. So fxyz, which is sine 3x plus yz. So let's compute fxxz. So means that you differentiate x twice and then differentiate z once. So let's first compute the fx. This is cosine 3x plus yz is 3, right? fxx is 9 negative sine 3x plus yz. You get another 3 out. Negative is from the cosine. And then fxz, this is negative 9 cosine 3x plus yz, differentiate with respect to z. So we get, this is a constant, 3x is a constant. We differentiate this, we get y. So the answer is 9y cosine 3x plus yz, right? I think this is about the partial derivative. So let's make a summary. So for function of two variables, three variables, I will not emphasize. You have to know it by yourself. We have fx, fy. We can write it in this form, or some book is writing in this form. Just just because there are so many notations. It's not my fault. Fx, Fy, this is called the gradient, right? And then we have Fx, Fxy is equal to Yx. Good case, but in general, we only deal with the good case. Fyy, we write it as a Hessian. F as Fx, Fxy, Fyx, Fyy. So this is called the Hessian of F, gradient of F. You may say, why to talk about it? If you recall what we studied for function of one variable, we want to know the maximum value and the minimal value. At that time, you say, okay, let's first find the critical point and then analyze the second derivative. Here, it's complicated. You know, we also want to know the maximal value and the minimal value. You know, in economy, you always know you want to earn as much as money you want, right? Where you want to increase the revenue as much as possible, right? If you convert it into math, that's maximal or minimal. If you have many variables, how do we deal with that? We will talk about this next week. Okay, we'll try to define what's the critical point for the function of many variables and how to analyze the second derivative. Here we call it a Hessian. Okay, when the point is a maximum point, when is the point a minimal point? Okay, we will talk about it next week. Okay, if you have time, you know, you can, you know, just prepare the next week's lecture. That's why I write the lecture notes, because I know if you just without any preparation to come here, it will be very hard to follow when, you know, follow the class. That's my own experience. When I was studying my undergraduate, you know, if I didn't prepare anything, I just cannot understand the professor are talking about. Okay, stop recording.